Hi folks, this is Gordon Parker from Michigan Tech, and in this video I'm going to do a brief introduction to Laplace transforms. First, a little motivation and then some goals of what you should be able to do by the time we're done with this. This video is a series on control system design, and Laplace transforms are used all the time in linear control system design. So it's really important that you have a solid grasp of Laplace. Now, if you have a differential equation model of a dynamic system and you're trying to design a control system for it, then once you get it into the Laplace domain, it's super easy to analyze the performance of it or the stability and a lot of other things once you close the loop. That is, use the output of that system to automatically compute the input. By the end of this, you'll have the basics of Laplace and inverse Laplace and be able to work a few examples. And certainly be able to use a Laplace transform table. Now, there's other videos in this series that go into the gory details of Laplace transforms and inverse Laplace transforms, partial fraction expansion, all kinds of things. Here, we're just going to scratch the surface. One way to think of the Laplace transform is it just takes a function of time and converts it into a function of the complex variable s. And we use this cursive L to indicate the Laplace transform. Anything inside the square brackets, any function of time, is what gets eaten up by this Laplace transform and turned into a function capital Y of s. The notation is typically lowercase letters for the functions of time and uppercase letters for the Laplace domain quantity. Here's the math definition for the Laplace transform. All you do is take your function of time, in this case y of t, multiply it by e to the negative st, and then integrate from 0 to infinity. What you're left with, because all the t's go away, is just a function in s. The Laplace transform is a linear operator, so it obeys superposition, which means that you can take the Laplace transform of two functions in time, here f1 and f2, individually, and then add them together to get the Laplace transform of the combined function, in this case, alpha times f1 plus beta times f2. If the superposition concept is a little foggy, I have some videos on that topic also. Like all good operators, we can invert it and get back to where we started. So in this case, in equation 4, we take the inverse Laplace transform of y of s and get back to y of t. And the notation is that you take the cursive L and put a little superscript -1. It's not indicating that we have 1 over L or something. It's just saying that we're taking the inverse operation. Here we're not going to go into the math of the inverse Laplace transform. It gets a little crazy and requires some complex variable background. Now, why would we do such a thing? Why would we go from a function of time, which is a very well understood thing, to a function of s, which is some complex variable? Well, let's look at that from a differential equation standpoint. You'll have to take my word on a couple things here as we're moving along, but I think you'll find this pretty powerful. So let's say we have this lovely second order differential equation where u is some input, maybe a sine or cosine or what have you. Once we take the Laplace transform of this, and we have to use the differentiation property that we haven't looked at yet, but we will, not in this video, but a little bit later, we get this function in 6. Look what happened. We went from a differential equation and ended up with a polynomial. So we exchanged some calculus in equation 5 for some algebra, and usually algebra is a little bit easier to work with. This is one of the reasons that we use the Laplace transform, but there's lots of others. What we're going to do is just kind of get warmed up with a couple examples using the formal definition of the Laplace transform. Then we'll take a look at the Laplace transform table and use that approach, which I think you'll find much easier. Okay, so we're going to take the Laplace transform of the impulse function, delta of t. And you just have to recall the definition of the impulse function. It has this property, really, that if you have some function f of t and you multiply it by the impulse function, delayed in time by t0 seconds, the magic happens, and what you get out is just f evaluated at t0. And what we're going to do is just use the formal definition of the Laplace transform and then recognize or extract from it the f of t and the t0. So here's the formal definition. I just took 3 delta t multiplied by e to the negative st and integrated. And now let's compare to the definition of the impulse function, and we can see that t0 is just 0 because our delta is only a function of time. It has no minus t0 in it. And the f of t is 3 times e to the negative st. So you grind through the definition of the impulse function and out pops y of s equals 3. In general, we have that the Laplace transform of the impulse function is just 1. What we're doing here is starting to fill out a Laplace transform table. So let's do another one. How about this h of t? It's some exponential function with a constant in front of it. And we're just going to grind through the, using the formal definition of the Laplace transform. We multiply that h of t by e to the negative st and integrate. Here, just combine things up a little bit. And now we integrate. So fortunately, taking the integral of the exponential function is pretty nice to do. And we just have to evaluate these limits. And we get this. Now I would highly recommend when you do this sort of thing that you very carefully write out these limits because some strange things can happen. But when you put in e to the negative infinity, you just get 0, and e to the 0 is 1, so it really just has the effect of flipping the sign in front of the c over s plus a. And now we have another member of a Laplace transform table. Now, armed with what we just did in the previous slide, we can now handle an inverse Laplace transform. Here we have a v of s that's of the same form as what we just did. So now we can compare the c over s plus a to the 6 over s plus 2 and start backing out what the different pieces are. That is, the c is just equal to 6. And the a is equal to 2. And so here's our v of t. Another thing I would recommend you do when you're playing around with functions like this and Laplace transforms is to sketch those functions of time. So here's what we get for v of t. It's a decaying exponential, and it crosses through 6 at time equals 0. All right, because when you plug t equals 0 into the v of t, you just get 6. But then it keeps going up to positive infinity for negative time, or whatever negative time is. Well, here's an interesting thing. Since the Laplace transform is defined as being an integral from 0 to infinity, we don't really care what happens to v of t for negative time. So another solution for v of t would be this, where we take 6 e to the negative 2t and multiply it by the unit step function. And here the unit step function is playing the role of annihilating v of t for negative time. And here is what that function looks like, where for negative time it's just 0. And when we're working with Laplace transforms, it's often, I would say, cleaner to multiply your functions by 1 of t. It just is very explicit then about what you're describing that function as being. It'll also help us when we start looking at time delay functions and the Laplace transform properties, but that's not in this video. Here's a snippet of a Laplace transform table. They're pretty handy. They'd let us just quickly go from functions of time to functions of s, but a lot of times you have to play around with the functions of time, multiplying them by scalars and, maybe breaking them up into pieces so that your function of time fits in with the terms in that Laplace transform table. They also let us go the other way. So once you have a function of s and you write it as terms in this Laplace transform table, you can easily go to the functions of time. But here's what you shouldn't do. Let's take a look at this function where we take the step function and multiply it by itself. Well, you know, a step just has 0 for negative time and 1 for positive time. So when you multiply 0 by 0 and 1 by 1, you just get zeros and ones. So two steps multiplied by each other are just equal to the step function. Which means that if I take the Laplace transform of the step times a step, I just get the Laplace transform of a step, or 1 over s. What that also means is this, that the Laplace transform of a step times a step is not equal to the Laplace transform of a step times the Laplace transform of a step. It's very tempting to extend that notion of superposition, which is the sum of functions, to the product of functions, and don't ever do that. In general, we can say this: the Laplace transform of f times g is not equal to the Laplace transform of f times the Laplace transform of g. Let's just do a couple more examples, and before we do this one, let's sketch it out. So here's the step component that has an amplitude of 7. Here's the ramp, and when I add them together, I get this. It's a crazy looking function of time, and we're going to take the Laplace transform of it. And all it is the Laplace transform of those two pieces added together. So this is superposition in action. And now we can write it as a single rational function, a polynomial in s in the numerator and a polynomial in s in the denominator, and we get that. Here's another one, pretty straightforward, but let's sketch it out. There's y, it starts out at 4.2 at time equals 0, and in my y of t at the top of the slide, I didn't multiply it by 1 of t, but I'm going to assume that it's multiplied by that unit step and being annihilated for negative time. It's a pretty quick little function, and when we take the Laplace transform of it, we get this little beauty. And one last example. And here we're going to take the inverse Laplace transform of this. Now when we go to the Laplace transform table, we hope that we find it in the table, and in this case we do. That is, we hope that we find 7 over s plus 5 in the table. There it is. And now we have to start identifying terms in the quantity in the Laplace transform table with what we have. So we can clearly see that a is equal to 5, but we don't have 5 in the numerator, so we have to break this out so that we do have 5 in the numerator, and that is multiplying it by 7/5. And now we can just write out v of t. Boom. Might be worthwhile to plot this. To plot it, one trick you can do is take a look at this function and say, well, where is it at time equals 0? So you let t equals 0 in there, and you just get 0. And then you ask yourself, where is it at time equal infinity? The e to the negative 5t term goes away at that point, and we're left with just 7/5. So here's our 7/5 line that we should get to in a very nice exponential kind of way, and there's v of t. Now, whenever I see this, I go, oh, that is the classic step response of a first-order system. It's a beautiful thing. It appears all over the place in engineering, and it is the solution to a differential equation that looks just like this one. V dot plus 5v equals a step with amplitude 7. Well, that's it for this brief introduction or perhaps review of Laplace transforms. We took a look at the math definition of Laplace transforms and used that to take the Laplace transforms of some functions of time. And then we got into the Laplace transform table, where we also looked at some things that you shouldn't do. Finally, using the Laplace transform table to take Laplace transforms and take inverse Laplace transforms. Well, I hope this helps. Thanks for watching. Bye-bye.